Alrighty. I am going to redo my uh my thesis defense. So let me go ahead and get that pulled up. I felt like I kind of stumbled through it a little bit, didn't remember a ton of it last time, so just gonna quick redo. Thesis defense slides 421. I wonder which ones are. I'm gonna assume the later one is gonna be my final version. Damn, that was last year. I did my thesis defense a whole year ago. All right, let me go ahead and start sharing my screen. Oh, don't want to end the meeting. Um, all right. Oh, I forgot to put myself in presenter mode. Let me see. Let me see if I can, what that'll look like. Share. I'll pop up in the corner. Yeah, I like that. I like that right there. Boop. Now I'm part of it. Yay. Okay. And slideshow. All right, ladies and gentlemen, welcome to my thesis defense that I delivered last year for my master's in electrical engineering with an emphasis in AI and machine learning. My thesis is over the XView dataset and object detection on that dataset using deep learning and super resolution images. This research was funded and sponsored by AFRL, the Air Force Research Lab, as who works in conjunction with the Credit Center at Prairie View A&M College. All right. Of course, you have my committee. So here we have the XView challenge. It allows us to understand the world in new ways when we take satellite or aerial images. The primary purpose of the XView detection challenge is to accelerate computer vision in the following four areas. Reduce the minimum resolution for object detection. Minimum resolution, of course, being the pixel representation of an object in an image. So as we'll get into later, small objects in this incredibly large 4K resolution image may only be represented by 16 pixels because cars are so small and the scale of an image can be up to a square kilometer. Of course, we always want to improve learning efficiency and time of convergence of models, enable discovery of more object classes. So this is also labeling and ties into minimum resolution, and then improve the detection of fine-grained classes. So uh, classes with lack of representation, as we'll see, the XView dataset does have a large instance imbalance uh, between the various classes. So some of the objectives and contributions of this work were to generate SRGAN images, SRGAN being super resolution generative adversarial network images, and then obtain YOLO versions. YOLO is not you only live once, it is you only look once, and this is a single stage detector model known for its high performance. Um, Let's see, provide insight into the model's performance, why it maybe performs how it does, identify strategies and architectures to increase the model's overall performance in future applications. My contributions included the exploration of SRGAN architectures and the current advancements in that area, examine the impacts of SRGAN on the XView dataset, application of satellite imagery and the need for reliable sources of identification. Usage of various YOLO models in the XView dataset, so we test various versions. Um, and then I provide analysis on how to possibly improve and how the architectural changes from version to version contribute to increased performance. And then we, of course, have potential growth areas. So some background information, object detection is a type of computer vision task that is used in a variety of applications, including automated vehicle systems, automated driving, surveillance, security, and medical diagnostic imaging. A famous one is during the COVID-19 epidemic, scanning X-ray images of the chest to diagnose patients with COVID. Different, although they could be, symptomatic, which was kind of cool. Different applications will determine the type of model and strategy being used. So in a security system, probably need like real time, um, low latency, versus, something that like an insurance claim may not need to be as fast, but more detail oriented. So you would use a larger model that has slower inferencing speed, but maybe delivers a higher degree of results, or higher certainty. Of course, you have the platform of deployment. So the size of the model matters when you're dealing with computational resources. Deploying the largest model imaginable on a Raspberry Pi that has 150 million parameters obviously is not a great idea. So using smaller models, of course, for the computational resources available is key, to optimization. So we have different types of detection models. We have single stage and two-stage detectors. The main difference is that two-stage detectors determine what we call an ROI, or regions of interest, and then perform regression on those areas of interest, or regions of interest rather. Like I said previously, YOLO is a single stage detector, and the one that we will be using and evaluating for this study. Let's see. Single stage detectors, how they differ from two stage. Instead of ROIs, they are split, images or inputs are split into a predefined number of boxes. It's like a grid-like structure over the image. And these are referred to as anchor boxes. Now, these anchor boxes, there are thousands of candidate boxes that are drawn, and then regression is performed on those. And then the anchor boxes serve as bounding box, like the original point, and then bounding boxes are drawn as offsets from those anchor points. So yeah. Here we just have architecture, what separates a single stage from two-stage detection. Input, backbone, neck, and dense prediction are all present in one-stage detectors. The difference is that two-stage detectors have a sparse prediction architecture added to them. Here we can see the region of interest being analyzed. You feed that through a CNN. Of course, it has weights and all that stuff. It does its convolutions, and ultimately, spits out its classification. Here we have the single stage detector SSD models, that this is a great image for the anchor boxes, the candidate boxes that are generated, and then the resulting bounding box. Typically, CNNs or convolutional neural networks are used when it comes to the task of object detection. Most object detection models are applied to more conventional looking images. We'll get into this a little bit later, that appear with in a very frontal view. And it makes learning features of the data easier, as there are just more features present in an image, versus aerial or satellite imagery, that top-down view of something. It becomes very difficult to discern, unique features about an object when you're solely looking from the top. So let's see what else. Sorry, I was checking my audio. It doesn't appear. Test, test. It doesn't appear that my microphone's moving, so I'm just curious whether. Huh. Well, I guess we'll see in the recording. Hope I didn't do the spiel for nothing. All right. Aerial imaging and its history, and then its various applications. Satellite imagery is a top-down view of observing Earth from any number of aerial platforms, including UAVs, drones, helicopters, and planes. And as early as the 1900s, there were use with cameras and pigeons to survey battlefields and enemy trenches. Various applications include, of course, detection of oil spills, natural disaster rescue teams, and damage appraisals in areas that experience natural disasters. irrigation and field mapping, efficient mapping for irrigation and farming. Of course, you have military applications such as target identification and things of that nature, and then environmental monitoring such as deforestation or urbanization. This is an example of the XView data set. And so just to highlight some of the difficulties that we experience, you see a picture of me. That very front, you can see eyes, nose, ears, mouth. You can see all these various features about me and learn to recognize me based off these features. Even if I change my shirt or maybe I trim my beard a little bit, not getting rid of it, but I do something like that, you still have various features, identifiable characteristics about me that that you can infer my identity from. From a top-down view, if I were to only show you the top of my head, you miss a lot of those unique identifying features, and that is the problem, a unique problem with aerial and satellite imagery, and part of the struggles of this detection, and why using object detection on these on this data in particular is so difficult, because we lack the details that we would see in typical imagery. We have the XV data set. So a little bit about the data set. There are 1 million data instances inside that set, spans across 847 images. And of those 1 million data instances, they are split into 60 different classes, including buildings, cars, cranes, excavation equipment, things of that nature. And they're often in very dense these images are usually very dense with instances. The data set has millions of annotations, again, over a mere 847 images. This is an average object count of nearly 1,200 instances per image, and often is higher just because some images are incredibly sparse and only have 1 or 2 objects in them. Sparsity present in some images, and this is a problem due to a number of predetermined anchors used by the YOLO model. The YOLO model actually has a genetic algorithm that does some evolutionary training to determine the appropriate number of bounding boxes, anchor boxes that should be present on images. And by doing like a sort of k-means clustering genetic algorithm, before training occurs, it figures out, again, those the average number of anchors that should be present in an image. Because there's such sparsity at times and then such high density, achieving a good number of anchor boxes isn't really realistic. You can get close though. Samples for training may have large portions of their pixels unutilized. So like I said, a car only takes up maybe 8 to 16 pixels in an image like that. And when you have a 4K image, that is a gross number of pixels that aren't utilized for detection. So it's a lot of noise that gets put into these models at times. And then you also have extremely dense areas where the anchor count may be insufficient to identify each object in a given area, because anchors are, if we go back to that grid, these grids are very large. I could fit several homes, hundreds of cars in a parking lot, all in this one anchor. That is incredibly difficult when it comes to identification. Some of the challenges that I've already gone over: 60 classes for detection in this data set. There's a large variance in object size. Some, as we'll see in the up and coming slides, we'll see just the range of various object sizes due to the scale being known. With each image, there's about a 0.3 resolution per pixel. So we see 30 centimeters in the real world per pixel in an image. Due to the scale being known and fixed, rotation of an image does very little, as the top-down view does not offer a variety of angles from which to view an object. So you can't do typical like data augmentation to grow that 847 image data set into maybe 1600 by rotating all of them 90 degrees or 180 because it's top down view. It just doesn't, or like translating anything, it doesn't necessarily add to the model's ability to generalize on that data set. Because orientation really doesn't matter in a top down setting. Um, and most angles are likely already captured in the existing data set. Little to no data augmentation is applicable. Tons of background noise complexity and blending between instances. And then we also have, as we'll see, a massive class imbalance. This is an example of the challenges and the tons of labeling that had to go into these images. This is, of course, is the ground truth. This was labeled by hand by a human, and they said this is a building, this is a car, this is an X, and we use this for training a model. Here is what I was referring to when it comes to size of objects and class imbalance. We see a small portion of the data set. Railway vehicles only occur at a 17% frequency and have a pixel representation of less than 100 pixels on an image. Then we have moderate number of, of other various classes that occur between the 100 pixel and 2000 pixel range, giving the model a little bit more information and features to use when it comes to generalizing and identification. And then, of course, we have the largest size category at 2000 plus pixels, and we'll see that massive class imbalance here as buildings are much more common. And so models have not only more data instances to learn what a building is because they're so large, they also have a higher number of features that they can learn and generalize off of. So it is expected to see a good performance from the building class, also maybe a bit of a bias in the model for it. Experimental challenges, the YOLO label takes time to parse and generate before usage, because they all come in, I think it comes in a massive JSON, or I can't remember exactly, it's been a while since I've looked at it, but the YOLO model takes an image and then an associated text file with the ground truth coordinates in it. So you have to parse those all into separate text documents for the YOLO model to use, and it's a pain in the ass. Training. Fuck. Fucking fly just. Anyway. Just attacked you. Training on images that are of course, this is the SR-GAN images. You can have images that are upwards of 14K to 16K resolution after they're generated and interpolated by the SR-GAN network. This is highly complex data, which requires small batch sizes due to memory constraints and the sheer size of these images. There are 847 images, take up over 300 gigabytes of memory, what typically would be kilobytes, just based off the massive size of these images. We have faster training for base images, but models with 150 million parameters still take days to converge. So working on even larger images that take up tons of memory, it took weeks. Using the largest possible submodels for these versions only exacerbates convergence time. Again, that 150 million parameters. And managing environments for different YOLO versions is painstaking work, as I had to have multiple Anaconda environments because of legacy code not being supported on certain models, and just version history being a pain, because when things break, it doesn't say, hey, you need to go update this version. It's just, they need to tell you that the code isn't supported anymore. You just got to go fish around for version number. It's not always apparent that it's version number either. Sometimes you think it's your code. Parsing of labeled images and IDs. The YOLO format for labels requires, this as I mentioned, an image.1, so an image name .jpeg, and then a corresponding image, same image name, and a text file with the ground truth in it. Data comes in a JSON file as raw text, have to parse millions of lines, separate all into TXT files with the appropriate labels. YOLO assumes that labels are in an array from 0 to 59. However, the XView data set comes with a separate labeling system. So for example, a building class is ID 73. But if I were to directly reference that in an array from 0 to 59, we get an out of bounds error. So there has to be some translation of the IDs that occurs as well. So that's just another hurdle to jump with this data set. A little bit about state-of-the-art object detection and satellite imagery. As previously stated, CNNs, convolutional neural networks, are traditionally used in image classification tasks. But one unique problem faced by traditional CNNs is the use of the sliding window technique, where the kernel checking small segments of the image at a time in overlapping passes. But a majority of images in the background are not used for detection, which leads to, guess what? Wasted calculation and computation. Just adds so much time to the models, like inference time. Not to mention specific instances with larger pixel counts can't possibly fit into a single pass of the sliding window, therefore not allowing for accurate object detection. If you have a tanker that takes up, 2,000, 5,000 pixels or something like that, that sliding window may only capture a fourth of that tanker and misidentify it because the window is not big enough, versus that window is perfect for a car that only has 16 pixels. And this ultimately just affects the spatial continuity of information, again, harming the ability to inference appropriately. So again, I spoke previously about data augmentation and how it's not really applicable to the XView dataset. But one of the methods that is available to us is a GAN, or Generative Adversarial Network. These are two neural networks that work in conjunction with one another in a zero-sum game, where they compete with each other for advantage and disadvantage or equivalent loss for each of the networks. And so you have an adversarial, you have a discriminator and a generator, right, in this adversarial network. The generator is trained to improve its ability to generate realistic data. The discriminator is trained to detect fake data. Okay, and so if the generator fools the discriminator, then the generator gets a point and the discriminator loses one. And then if the discriminator determines that the data is fake, then of course the discriminator is rewarded and the generator is ultimately penalized. Which then it will go through, of course, you have the gradient descent where it'll adjust its weights and attempt to make more accurate, realistic data. The discriminator is typically a CNN that is pre-trained on real data, and then using GANs allows researchers to generate synthetic satellite imagery that closely resembles real satellite imagery, so you can generate fake data as well as enhance real data. So a little bit about the SR GAN images and architecture. You have some noise or low resolution input into a convolutional network, and then ultimately you put out a super resolution or high resolution output. And this ultimately gives you a higher pixel count per instance. You have more pixel representation from smaller classes. So instead of a car being 16 pixels, it has now, I don't know, 64 pixels, which gives the YOLO model more features to learn about that instance type, that car, allowing for better generalization and better recognition. And this also aids in distinguishing objects from backgrounds. Just because, let's say you have a white car and it's snowing outside, if there's not clear delineation between the foreground, the background, and the target that's attempting to be inferenced on, well, the computer can't see it because there's no edge detection occurring. You can't see, you just can't see it. And then you have the discriminator, which takes in the super resolution image or high resolution, and then determines whether it is real or fake. Some of the advancements here, I recommend using ESRGAN, which is enhanced super resolution generative adversarial networks. Um, it has a deeper and wider architecture than SRGAN with more convolutional layers and larger feature maps. This allows ESRGAN to learn more complex and intricate features in high resolution images. Um, it has a unique perpetual loss function that incorporates both content and adversarial loss functions. Um, this new loss function allows ESRGAN to better preserve the details and textures in the low resolution input images. There's also a lower artifact rate when compared to SRGAN. So some of that interpolation, sometimes it inserts it doesn't know what to do in these times of interpolation, and it produces artifacts that are somewhat inconsistent in the real world and things you wouldn't find. Here's some examples of that. Moving on to the YOLO architecture, you have the spatial EELAN pyramid, which is responsible for it's a feature pyramid. You have the three heads for detection and bounding box coordinates. You have the let's see, the feature pyramid network, and then the YOLO specialized loss function, which we'll get into a little bit later. So technological updates and differences between the models. YOLO 4 is the first to introduce trainable bag of freebies with optimization methods. YOLO V5 introduces model scaling on top of trainable bag of freebies. And YOLO V7 introduces the layered aggregation networks and model reparameterization. And then these are the size of the models that we used. YOLO V4, with YOLO V7 being the largest and most parameters. Trainable bag of freebies and hyperparameters. So hyperparameters are important to the machine learning process because they control the complexity of the model as well as how it learns. So some hyperparameters significantly affect convergence time. Examples of these would be the learning rate, the batch size, the optimizer that is chosen, and then of course you have things like the dropout rate and things like that to introduce some better training to them for the model. That way, certain nodes and branches don't develop too high of a weight that all decisions are necessarily based on a single weighted layer. Um, the trainable bag of freebies works in tandem with hyperparameters for a lot of the optimization of the model without altering the architecture. And some of these things include mosaic data augmentation, label smoothing, and cut mix, where literally like you crop photos, you crop parts of photos, slap them on other photos. Mosaic data augmentation, where you use multiple photos, combine them as a whole to make a larger photo and learn that way. And then to get into YOLO V5 and model scaling, adjust the number of layers and channels in the neural network to match the resolution and complexity of the input image. This is great for SR super resolution data because the channels needed for such large data do need to be scaled. You have various versions of the models are available, with the largest and most complex having the most layers and channels, making it a bit better suited for high resolution images. Adjusting the number of layers and channels depends on specific requirements of the tasks and ultimately affects the speed and accuracy of inferencing. And then YOLO V7 is the first to introduce cross-state partial networks, where memory resources are utilized that keep previous layers in the memory along with the distance from the gradient. Previous research suggests that the shorter the gradient must travel results in overall a more powerful network. We use a CNN to extract features and creates part of the cross-state partial network, each of which predicts a part of the segmentation task. And they also utilize parameter sharing with some uniqueness, and the consistency network concatenates. You have EELAN and reparameterization. You have efficient and effective long-range attention network, and this builds on the cross-state partial network architecture. ELAN uses expand, shuffle, merge cardinality, which promotes cross-channel interaction and improves the representational power of the network. The EELAN, the EELAN, the CNN feature maps are first processed by spatial pyramid pooling for global context information, and then reparameterization, complex probability distribution into a simpler one, easy to apply statistical methods for analysis. Here we got some model comparisons in various sizes, their average precision, their size, and number of parameters, things of that nature. Some metrics for evaluation include precision, recall, and F-score, where the F-score is the harmonic mean of precision and recall. Oh, and then of course, I don't know if I skipped over this, but mean average precision, all used to determine the efficacy of models. So we have the YOLO v4 results on base data. You can see it works very well on the distinct features of a plane. Just imagine a plane shape is very unique, distinct edges, and usually they're on like black tarmac, and so easy to distinguish various colors. Like YOLO v5 base data again loves passenger planes, and YOLO v7 loves passenger planes. These are the image, the IDs associated with the XView data set. So it's a bit of a, again, that's that translation that I was talking about from the XView data having unique IDs to the YOLO having an array of 0 to 59 object classes. All right. The analysis of the base results, the unique challenges in the XV data could not be overcome by architectural and added optimization features in the newer YOLO models. All these models fare relatively the same on the XV data. New strategies didn't produce any statistically significant change from model to model. And so new strategies must be employed as changes in each model's architecture proved to be insignificant for this task. My recommendation would be to enhance data further, or some sort of ensemble learning technique may need to be employed where multiple models are trained on this data and each one specializes in a unique area. Some of the results for YOLO v4 on the SR data, planes still perform very well. However, a lot of the other classes don't. We actually see a significant drop off in a lot of and results in a significantly lower mean average precision. But yeah. So analysis of the super resolution results, the mild degree to which performance improved between super resolution results was due to the advancements made in model architecture. However, these were mild at best, mostly insignificant changes, and due to other forms of image enhancing GANs presenting better results than vanilla SR GAN performance, it makes sense that we may want to explore ESR GAN in the future. The performance on the vehicle lock class instances exceeded the anchor box size and therefore led to inappropriate classification in most cases. Performance improvements will likely be derived by creating larger anchor boxes and enhanced SR image super resolution images. So in conclusion, the XV dataset presents many unique challenges not seen in typical computer vision and deep learning applications. The performance improvements generated valuable insight when considering the improvement of YOLO models on satellite imagery. There is about a 0.05% increase in the mean average precision from model to model on well-performing classes such as passenger plane, but virtually no improvement on other classes. Advancements in super resolution imaging are astonishing, but don't fit the YOLO architecture. Therefore, other data augmentation methods may be needed or other models be explored. This study paved the way to gain understanding of the type of specialized models that are required for this task. So some of the future work I would propose most importantly, I'd like to highlight the Swiss AI development of several models that take various instance sizes. So they have a small model for instances less than 100 pixels, a medium model for 100 to 2000, and then 2000 plus you have a larger model. They actually train 3 separate models to detect on this data. Again, using ESR GAN to generate even higher resolution images, and then just continue to find ways to improve data quality. Mostly that mosaic data augmentation, cut mix, and things of that nature, I think will continue to aid in a model's ability to generalize on the XView data set. I'll go through some of the backup slides. So one of the hyperparameters I mentioned was the optimizer, and the atom optimization algorithm is based on traditional stochastic gradient descent, where you update network weights iteratively based off the training data. You don't wait for entire epochs to finish before updating weight rates, which ultimately introduces more noise, but will allow for faster convergence. A learning rate is maintained for each network weight parameter and separately adapted as learning unfolds. There's not a universal rate, but is optimized during training. Adam takes advantage of both AdaGrad, which I would have to do some more research on. I don't remember exactly what that is. And then root mean square prop. This algorithm calculates an exponential moving average of the gradient and the squared gradient, giving it's an adaptive learning rate calculation. Also, this includes decay rates for these moving averages, and more weight is given to recent gradients as compared to historical ones. And here we have the training costs. K-means clustering and genetic algorithms, of course, are used to determine the appropriate number of anchor boxes for images. K, you select K number of initial centroids randomly from the data points, and hence the K means. This K is indicative of any number. So you can have 4 means clustering, where this data set, instead of 3 groups, is split into 4 or 5, and different centroids are chosen. Excuse me. And then you assign each data point, okay, each instance, to the nearest centroid, creating ultimately K number of clusters. Each centroid would be near the middle of the data. And this is a simple Euclidean distance between each data point. And then, this green dot is closer to the center of this data group, this centroid, than this data piece is from this one. So this gets calculated from this centroid and that centroid. Ultimately, the centroid's closest, so it's grouped in with the red group. You can recalculate centroids of each cluster by taking the mean or the average of the data points in that cluster. So you add up all these values in some way, and then take the average. The average would be about right here. This is probably where the centroid would lie in this data set. Is kind of the center where they all congregate. Repeat steps 2 and 3 until the centroids no longer move significantly, or the maximum number of iterations have been reached on the data. And then minimize the sum of squared distances, Euclidean distance between data points and their assigned centroid. Yeah, the goal is minimization here. Then you have genetic algorithms, which is a type of evolutionary algorithm based on the principle of natural selection and genetic inheritance, very Darwinian, if you will. It is a computational method that is used to find the optimal solution to a problem based off the survival of the fittest. So a selection is a subset of the population selected to reproduce based off of their fitness or quality of solutions, with higher fitness values being more likely to be selected for reproduction. And then just like in actual survival of the fittest, you have some crossover you have crossover, which is like the reproduction, and then mutation, random mutations that occur in genes. Um, Yeah, crossover, of course, creates new offspring solutions, and then based off of the already high performing parents, and then you still have the parents that are used. Then you have crossovers and some random mutations that are thrown in there to create genetic diversity in the offspring. And ultimately, during each epoch or iteration of the genetic algorithm, um, the highest performing um, the highest performing offspring will be pushed on, crossover and mutation occur until we start to see that future series of offsprings are all they've somewhat reached an optimized performance. Um, and you have stochastic gradient descent versus traditional gradient descent. So the difference with stochastic gradient descent being used as an optimization algorithm, and it's attempted to minimize the loss function. But the difference here is that it computes and updates weights based off of a loss function and steps in a direction to minimize that loss function. It's faster than traditional gradient descent, which occurs at the end of an epoch, one massive update, versus stochastic gradient descent is smaller steps and individual updates along the series of an epoch, which an epoch, I probably should have said this sooner, is an entire iteration of a data set. So in the XV data set, it would be a full iteration of the 847 images. However, stochastic gradient descent produces increased noise in the data as the weights fluctuate more consistently versus you go through an entire data set, it stays somewhat consistent, one massive update, and then we see changes. Um, and So again, so this is indicative of a loss function, okay? This graph represents a loss function, and ultimately what we want to do, the loss function, there are different loss functions you can use, but ultimately what the loss function measures is the difference between the real world data and or the ground truth and what was inferenced. Um, then you almost subtract the differences between the realistic expected value and then the generated value, and that loss um, is then quantified, and we want to minimize that loss because by minimizing that loss, by minimizing approaching this minimum, we're modeling the real world environment more accurately. That means the lower the loss, the lower the difference, means the closer we're encroaching to being hyper accurate, hyper real, um, and being indicative of the data set. So you have activation functions that are used in models. One of the common ones is ReLU. This is because it's computationally efficient and takes the maximum of 0 and the given input. It is nonlinear and therefore allows for complex mapping. There's some sparsity with it, so only some neurons are activated for a given input, resulting in lower computational costs. Again, that's that 0 versus given input. So it's going to activate or it's going to be 0. So therefore, it's just we you don't have to consider certain things because certain neurons are never activated. Avoids the vanishing gradient problem, and it's easier to interpret and debug just because you either get an input or it's 0. Another means metric of evaluation is IOU. Great for determining the cost or the loss function is IOU. This metric is used to evaluate the object detection models and measures the overlap between the predicted bounding box and the ground truth bounding box. So let's say I have here a great. Do I have a marker? I do. So this is, forgive me. We have a box. This is, oh my fucking God. The camera's flipped. Okay, so you have a box. Oh my God, I'm going the wrong fucking direction. Shit. All right, I'm gonna just draw this real quick. So you have a box, right? And this shaded in portion is the overlap, all right, the intersection. And then the union of these two boxes, the sum, the total area. So we measure that the point where they intersect over the union, over their total area. And this is again can be directly used for a loss function, determine how much overlap there is between the inference and the real life data. Some other evaluation metrics include classification accuracy, the percentage of correctly classified images in the data set, and then the mean squared error, which is a regression metric used to evaluate the accuracy of predicted values. It calculates the average of the squared differences. Okay. Um, so again, that's difference between the expected, what was generated, square it, slap it over an average. Then you have the XV2, and I actually can't read this because it's in the way. Mute myself. XV2 and its use cases. XV2 is a large scale data set used for object detection, consists of high resolution images of 60 different cities around the world. Um, and in a range of lighting and weather conditions, it's a massive repository of damaged buildings after natural disasters and can be used for damage analysis applications such as for rescue teams to get in there, identify areas particularly impacted where survivors could be, and then of course insurance claims after the fact. Hyperparameter optimization. Different ways that you can optimize your hyperparameters and allow for the most efficient means of convergence of a model. That includes the grid search, which is creating a grid of hyperparameter values and evaluating each uh, model performance based off each combination in that grid. You have the random search where you just select random hyperparameters until you find some that are working really well together. You have some Bayesian optimization, which uses a probabilistic model to estimate the performance of each combination of hyperparameter values and then select the combination with the highest expected performance. Then you have, of course, evolutionary algorithms, which populate candidate solutions, as we discussed, then apply evolutionary operators such as mutation and crossover to generate new candidate solutions. And then of course, the best performance continue to pass on until you reach the most optimized version. Here we have a YOLO loss function where C is the class confidence and the lambdas are constants for the coordinates of the bounding box. Here we can see again that loss that I was referring to. You have xi, which is the x input, right? Um, of the bound fuck. It's like the ground truth, right? And then you have like the predicted value, the generated value. Find that difference, square it. And these are, of course, the differences between the they're quite literally grid coordinates. So you have the ground truth in that text file, and it says that the x coordinate, the x start of this bounding box should be at pixel 56. But the model starts it at pixel 58. Okay, so there's a 2 pixel difference. We square that, and then we do that in the y direction as well, and ultimately derive the associated loss, the inaccuracy between blah, 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 between the generated and expected values. Of course, you have some references, the work that came before me on YOLO V3. And that is it. Thank you for attending. Please leave any comments, questions, and any other topics you'd like me to cover, whether that is philosophy, politics, other computer science, and vision tasks. Thanks again. Body, yada, 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 yada. Oh, fuck. Did I end the recording? No.